So this video is by no means comprehensive. It just serves as an intro to the technique called gas chromatography, mass spectrometry, or GCMS. And GCMS is really just, it's considered what's called a tandem technique. Tandem or hyphenated techniques are literally because you're coupling one technique with another through a hyphen. And so in this case, there's really two different instruments here. One is the GC, and in the schematic I have here, this is the GC portion, and then the latter part is our MS. And so the GC is focused on separation of gases, gas molecules, and the MS is focused on analyzing those molecules and really counting or detecting. And so the MS is really serving as the detector here, and GC is the front end, just serving as the separation. So the previous mass spectrometry videos focus on exactly how the MS works. So I won't go into great detail here, except that there's just a transfer line that's under vacuum that takes your compounds after they've been separated on the column and injects them into whatever the ion source for the tool is. So I'm going to show you a sped up video really quick on how the GC part works. So this is an example of a GC. It looks pretty similar. This is an older version of what we have, probably about 10 years older than what we have. And then there'd be another large box affixed to this through this panel right here, and that's where it would connect to the detector, in this case the mass spectrometer, not shown here. So this is just highlighting the GC part. So inside you've got this oven. That oven is temperature programmable, and inside of that oven is a column. And so as you inject your sample, and we'll show you where the injection occurs, your sample is typically in a liquid form. So it's often like an organic species that can volatilize, but is not volatile at ambient pressure and temperature. And so what you do is you inject them as a liquid, as a plug at the beginning. That's your mixture. And then this oven can be programmed to ramp at a particular rate. It can hold at certain levels, etc. And so your sort of first component of separation here is that as the oven ramps to various temperatures and hits the boiling point of various substances, once those things boil, they're then capable to move through this column. This column is an open tubular capillary column, which I talked about in the separations video, where it's very, very fine capillary, tens to hundreds of microns, very long, 10 to 20 meters, 50 meters sometimes, and only the outside or the interior wall of the column is coated with the stationary phase. Most often that's a nonpolar phase, but it doesn't have to be. But most frequent use of GCs are nonpolar, which means that you're going to then separate your compounds as they volatilize in the oven. They're then going to interact with that stationary phase based on their own nonpolar character, and then elute through the column. And then after they elute through the column, they'll go on to whatever the detector is that's connected here. So we have an injector, and then in this case the detector is built in, but you could imagine replacing this with the mass spectrometer through a transfer line here. So in this case the mobile phase for gas chromatography is of course another gas, and there's different things that are used, but the most common is helium, some inert gas that is not going to be affected by the ramp rate and is not going to react. Sometimes people use hydrogen. There's reasons to use one or the other. It's not important in this intro video, but helium is what we typically use. So you can see that we inject these things, and in this case the signal that's generated at the detector generates our chromatogram in real time. The injector can have a variety of different geometries, but generally you have something that looks like this, where you have your helium coming in here, so the mobile phase enters here. The rubber septum is the place where a needle or a syringe can insert a very small controlled volume of your sample into this system. And we can run this in either a split or a splitless geometry. A split geometry means that we can actually allow some of our sample to sort of cycle out and not be collected on the column, and that's important if you want to think about the Van Deemter expression where if we minimize the total amount of our sample that's injected on the column, we will minimize the band broadening effect from that component. And so for highly concentrated samples, we run it in a split geometry and open this port here, so we're only collecting, and we can control this, so we're essentially doing a gas phase dilution where we say we collect maybe 1 part out of 50 parts, so we do a 1/50th dilution. If you have a very dilute sample and you're doing this analytically, then you can close this off and use what's called a splitless injection, which allows you to capture all of the molecules, or within reason, on the column. So this is just showing you the function. Here's the helium gas. This is the process by which the dilution can occur. And they're showing you that the injector is hot. So when you inject the sample, it's almost instantly, you can see some portion of it was lost. That's the split type injector. So the injection manifold is typically set to 200 or 250 C, which means that right upon injection, everything is volatilized almost instantly, so that it can be diluted in that split geometry of the injector. The column is this capillary column, as I mentioned before. It's an open tubular capillary, so you have your helium mobile phase that carries your mixture onto the column if it's volatilized. But remember, this whole thing is in a temperature programmed oven, so we start usually around 30 C, and then we slowly ramp this thing up. So you can see the chromatogram as it's produced, as those different bands evolve. And the longer they're there, the broader the signal. The detector, one common detector is the flame ionization detector, FID. The way this thing works is you have some hydrogen gas, some flammable gas, and air mixing in here that will allow for a combustion reaction to occur. So you've got your sample, which is typically an organic, which is why FID detectors are good for like GCs that run adjacent to synthetic labs, because you're mostly looking at carbon and hydrogen products, maybe with some halogens incorporated. And what you do is you essentially burn these things and you create an ionization stream. And then you have some electrodes in here, and that just generates a little bit of current signal through some sort of squirrel cage type device, a dynode type device, and we get some responses fed into an amplifier, and then that is generated into our chromatogram. So this is the basic function of a GCMS, or a GC, I should say, which then would be coupled to an MS here if this FID were not connected. So the temperature programming in the oven here is pretty critical because it allows for an additional component of resolution of our peaks. So I'm showing you two identical mixtures. This just comes out of your textbook. Two identical mixtures and their chromatograms. In the top we have an isothermal system, meaning that the oven was just set at 150 and held the entire time. So you inject, everything sort of comes onto the column, and then you get sort of this crowding right at the beginning for all the very volatile smaller molecules. So you see C8, C9, C10, and then the longer ones start to have a little bit more resolution and a little bit more tailing, especially the stuff that takes a while to boil, because it takes a lot longer to get this stuff off the column. So you get this sort of asymmetric tailing effect. But you can see that as in a temperature program state, 50 to 250, 8 degrees per minute, you get this additional sort of order in terms of how the individual peaks are resolved, simply adding another dimension of separation here. So you've seen two detectors now. You've seen the mass spectrometer and you've seen the flame ionization detector, two of the most common that get coupled to a GC. And FID is far, far cheaper and easier to maintain. And so you can buy a GC FID on eBay now for probably $300, $200 and get it up and running. They're pretty easy and pretty robust. GCMSs are of course going to be more expensive because of all the vacuum equipment, the cleanliness, the electronics that are required to drive that thing. This comes from your textbook, just showing you different detection limits and linear ranges of different detector systems that can be implemented. So there's the FID on here, the flame ionization, it's got a pretty low detection limit, 2 picograms, and you've got a linear range of 10 to the 7, and so that makes it a pretty robust workhorse there, because it's got, you know, roughly 10 million factor change in the concentration, and it would still be linear, which is better than the mass spectrometer on the bottom here, which has a lower detection limit, presumably if you're using a splitless type injection or direct injection method, but it's got a little bit smaller linear range. And then there's a variety of other things that become much more specialized depending on the types of molecules that you are trying to detect. And so like electron capture is a really popular technique if you are looking at things that when ionized can form these radical species. Things like halogens. It's not important that you know all of these, I'm just giving you some perspective here. So the GCMS is a workhorse, especially for the organic chemist, because it's very simple to use. You can take your reaction mixture, as long as it's dilute enough, you can inject it directly on the column, and you can get identification and separation of most of the things that are present in your system, because you're fragmenting those compounds with an electron ionization detector. So, you know, comparing that against a library, you can pretty quickly identify what you have or have some probability for what you have, and it'll show you how clean your system is. The downside of GCMS, as you can imagine, the way that it works, you have to have a sample that's amenable to heating to get it into the gas phase. So if you have a thermally labile compound that wants to decompose when you heat it up, it's not going to last inside of here. It's going to break apart long before it gets in here, which is going to make identification difficult. Or sometimes you can have stuff that just, it doesn't boil readily, and so if it's got a really high boiling point, so it's a large molecular weight thing, like you'd never put a protein on here or polypeptide, because you'd never get it to volatilize before you just create a charred mess and you gum up your column. And so it's really good for small organics from an analytical perspective. It's a super robust instrument, highly sensitive, especially with a mass spectrometer, very low detection limits, which allows you to quantitate small organics pretty conveniently and over a fairly wide range. But you're, again, limited to this technique to something that's volatile. So there are a variety of methods out there where even GC, because a lot of people don't have an LC, which is a liquid chromatograph, which I'll talk about in the next video. A lot of people don't have one of those because it's maybe not cost effective to have both. We have both at CC. And so what you can do is take a molecule and you can undergo some sort of covalent modification of that molecule, which is going to render the originally high boiling point molecule into a state that's more volatile. And so those types of reactions are called derivatization reactions, and they're really common in the literature, where you'll see, you know, I want to measure like fatty acids, which are not good for gas phase analysis via GC by themselves, but you can undergo a derivatization process that has an acronym called FAMES, F-A-M-E-S, which will derivatize the fatty acids in a way that they become much more volatile, and then you can analyze them by GCMS instead of using an alternative technique.